So that's going to be the mass of 9 kilograms times the final velocity. And doing the fancy math there, you end up with a final velocity of negative, depends on if you're a decimal or fraction fan, equals negative 0.2 repeating meters per second. So after they collide, they're going to continue in the negative direction, crawling along. Let's just do a quick and dirty problem for you. So if I have a 3 kilogram mass going to the right at 4 meters per second, and I have a 2 kilogram mass going to the left at 5 meters per second, that's pretty much the same problem. Let's make something different. Let's make that 6 kilograms and 1. Make that 5. All right. Stop in there. So 3 kilogram mass going to the right at 5 meters per second, 6 kilogram mass going to the left at 1 meter per second. In which direction will they, if it's a perfectly inelastic collision, in which direction and how fast? In other words, what's the final velocity? So if you're not sure of the steps, there's an example right over there. When you think you have the answer, just give me a nod or a quick raise of the hand or. Okay. Is that a nod back there, Luis? Kind of like tipping at a bar for this sort of age. You know, if they don't see you put the money into the tip jar, does it really count for anything? It does count for something. Oh, that was the nod for this one. Sorry.
I know if you saw my nod earlier.
I did not actually. So
I know.
all right. Give another moment here. We'll see if we can pull this next bit off. All right, in unison. 3, 2, 1.
1 meter per second.
Oh, that was much better than I was expecting. That it is 1 meter per second. So we have 15 Descartes here, plus negative 6 Descartes, so 9 Descartes total. That's the total momentum before and after. And so if I do my after, 9 is equal to my total mass, which is 9 kilograms times my final velocity. And it is indeed still going in the positive direction, as I just defined it right there. That was encouraging. All right. Let's do a perfectly elastic collision. Yes. Oh, I'll tell you right now that on the last test, there will be a problem with 2 objects colliding into each other, and there will be a perfectly inelastic setup and a perfectly elastic setup. I'm telling you right now, there will be a test. There will be a test question where you have to solve for the final velocity for perfectly inelastic and the final velocities perfectly elastic. I think I said that right. Hopefully the intent is there. Let's do the same actually let's do one where the numbers come out much better than that. So 4 and 8. All right. So we're going to start out with some different examples here. All right. So I got a 4 kilogram mass heading to the right at 10 meters per second. I have an 8 kilogram mass also heading to the right at 1 meter per second. Make sure I got the numbers the way I have them in there. All right. For you Mad Max fans, and if you haven't seen Mad Max, then that reference means probably nothing to you. Okay. As with any of these problems, first figure out what's the total momentum beforehand, because we need to figure out what the total momentum afterwards is. So what is the total momentum before?
48 newtons a second.
Okay. Pause. Is there anyone who needs to ask about where the 48 comes from? I think I worded that very awkwardly. Any questions? Especially how Ethan came up with 48? Or perhaps he has a mathematical Tourette's and he's just shouting numbers out at random. If you are, that's a way to hit it perfectly. All right, it is 48. What's my total momentum after the collision?
48.
Yeah. All right, we're dealing with a perfectly elastic collision. So I know my kinetic energy is conserved. This is not conservation of energy, it's conservation of kinetic energy, which happens only in very special circumstances. So I need to know what the formula for kinetic energy is. And all of you know it at this point. So we are going to ask that question. If you need to do a quick look in your notes, I can song and tap dance for just a little bit longer before I finally ask that question about kinetic energy. Luis is giving me the finger there. Index finger.
Is that? No. Okay.
Yeah, what's the formula for kinetic energy?
1/2 mv squared.
That was very nice, although it seemed very silent over here. All right, so I have 1/2 mass of, now the subscript I'm gonna use, it is helpful to me to use a subscript that has some meaning to the problem itself. I could do subscript 1 and 2 or A and B. It's a 4 kilogram mass. I'm using subscript 4. Times the initial times 4 initial squared plus 1/2 m8 v8 initial squared. That's my total kinetic energy beforehand. And that's going to be equal to my total kinetic afterwards. M4 v4 final squared plus 1/2 m8 v8 final squared. And I know that the 48 Newton seconds, that's going to be equal to mass of 4 times V4 final plus mass of 8 times V8 final. I know the masses, I know the initial speeds, or initial speeds. I have 2 equations, 2 unknowns. This should be mathematically solved. Let's plug in numbers. Or do you want to get rid of the 1/2s or keep them?
Keep them.
All right, we'll keep them. So I have, that's a 4 kilogram mass, so that's 2 times V4 initial, so that's 2 times 10 squared plus 4 times 1 squared is equal to 2 V4 squared, V4F squared plus 4 V8F squared. Again, doing the fancy math, we get 204 is equal to this. Up here, that's going to be 4 V4F plus 8 V8F. because there's a bunch of subscripts here, I want to be able to avoid some careless errors. So I'm just gonna make a quick little substitution there. I'm gonna let, see, we're not using, what we're not using, how about we use S is equal to V for F, and T is equal to V8F. Just so I don't have to keep writing subscripts. So my problem is 48 is equal to 4S plus 8T. And the other equation is I got 204 equals 2S squared plus 4T squared. Two equations, two unknowns. How do you solve it? Or perhaps, how should it be solved? All right, first off, have I made a careless error? Or question, Ethan, you have a look on your face like there's something amiss.
No, I'm just trying to figure out where we got two equations from.
Where we got,
Two equations from.
the first equation is conservation of momentum. And the second equation comes from the fact that it's a perfectly elastic collision, so my kinetic energy before equals total kinetic energy afterwards. That's where we got the two equations. Okay, so I got my two equations still in notes using my shorthand with S and T. How would you solve it?
Isolate a variable.
Okay, which one do you want to isolate?
S.
Okay. I recommend isolating it from the linear equation, not the one with quadratics in it. All right, so I have 48 minus 8t is equal to 4s, and therefore this is 12 minus 2t equals s. Now what?
Oh yeah, that's another one.
All right, so I have, I'm just gonna divide everything by 2. It doesn't usually work as nicely as this, but I can do it this time. So I can just divide by 2 to get 102 is equal to s squared plus 2t squared. Now we plug in, so 102 is equal to 12 minus 2t squared plus 2t squared. So I'm squaring a binomial there. So I have 102 equals something plus 2t squared. So what is that? 12 minus 2t squared. Pardon?
48.
Not 48. Or if it is, it's coincidence. Let's flash back. If I had a minus b squared, what does that equal to?
A squared plus 2ab. What?
Minus 2ab.
Yeah. Plus b squared.
Say it again.
Plus b squared.
Okay. So it's the first one squared, last one squared, and then, since that's a negative, minus twice the product. So this would be 144 minus, let's see, 12 times 2 is 24, times 2 is 48, minus 48t plus 4t squared. We have a quadratic here, so I'm going to get it into standard form. I have 6t squared 0 equals, I have minus 48t, and then 144 minus 102 minus 40, oh, sorry, plus 42. Now what?
Formula?
Pardon?
Quadratic formula?
Okay, we can do it that way. So, t equals 48 plus or minus the square root of 48 squared minus 4 times 6 times 42 divided by 2 times 6. There are two answers and I do need them both. They both have meaning.
Seven and one.
Said 7 and 1.
Mhm.
So 7 and 1. So t equals, and so if t is 7, s is equal to -2. Just plug it in here. And if t is 1, s equals 10. All right, I know immediately that, or I have a lot of faith in what she's done immediately. All right, let's think about what the two solutions mean and why I know at least one of them is exactly what I was expecting. And I'm not counting the fact that I have the answers written right down here. All right, so which of these would be the actual answer to the problem? Sorry? Why is the bottom one the answer?
Because they're still moving in the positive direction to the answer with the negative. Or no?
Well, I mean, they're not necessarily going to be moving in the positive direction after they collide. Well, while he's thinking about it, anyone else want to chime in with which one is the actual correct answer to the velocities after they collide?
-2.
The 7 and -2?
Yeah.
Why? Hint, you are right. That is the correct solution. Why is the... Do you have an answer? I was going to reframe the question.
I don't know, that's-
All right. Why is the second solution not the correct solution for what their velocities are after the collision?
If they collided, they can't be moved. If they collided, they can't, I mean, it couldn't be 10,
Why not?
but they just collided. When something, hits or,
I could hit something and make it go 10 meters per second. Even at my age. As long as it were small enough. What is the physical meaning of that second solution?
Once it hit, it remained the same velocity, because it's already going at 1 meters per second.
Because what we asked here was, I have these two situations, and so mathematically said, I want another situation where my momentum is the same and the kinetic energy is the same. Well, one of the solutions is they haven't hit each other. They're still moving along like this, and it's all before the collision. So what an advantage of this technique. It's a pain if you don't like quadratics, but you solve the quadratic, one of the solutions will be the original problem. And this is why I had confidence that what Kelly told me, something had gone right, because I expect one of the solutions to be they hadn't hit yet. But because they hit, it's not going to be this. Their velocities will not stay the same after they collide, because that would mean that this 4 kilogram mass hit it and then kept going faster than the other one did. So they would have to pass through each other. So this is the solution, so my V8 final is 7 meters per second, and my V4 final, -2 meters per second. So that 4 is gonna hit the 8 and then bounce backwards. So, something like that. With better hand-eye coordination, you could probably do it better. Well, anyone would. Now suppose, questions before I talk about a different way of approaching the same problem? All right, let's suppose you're not a fan of doing quadratic formula. Some reason, your parents split up over arguments about the quadratic formula. It just brings back some really horrible memories. What can you do? Well, here's what you can do. What I'm gonna do is I'm gonna keep it in generic terms. I have some object A, I have some object M1 traveling initial velocity of A. I have some object M2 traveling initial velocity of B. They are going to collide in a perfectly elastic collision, so this is before. And then after, M1 is going to be traveling at some velocity C, and M2 is going to be traveling at some velocity D. So in essence, mass 1 initial, try that one again. V1 initial is equal to A, V2 initial equals B, V1 final equals C, and V2 final equals D. It's a lot of mess of subscripts, and I want to simplify it. I have two equations I'm working with here. I know momentum is conserved. So M1A plus M2B equals